16.7 is about change of variables for double integrals and triple integrals, although we will just do the double integral case, all right? So, I mean, but haven't we done this change of variables already? Well, not the way we're going to do this, because you guys know how to do a U substitution, right? You learned that in Calculus 1, you use it a lot, then you apply it infinitely many times in Calc 2, and we have done a lot of those U substitutions here in Calc 3, all right? But I mean, how can we generalize this idea of change of variables? Well, a picture first. Okay, so suppose you are evaluating this integral from of 2 times the square root of 2x plus 1 from 0 to 1. Well, again, what does that integral represent? Well, that represents the area under the curve given by the function in the integrand, all right, from the between 0 and 1 having our bound. That's why we needed this checkpoint concept so we can see what we're doing. But I mean, what do we do when you do a U substitution? So the purpose of a U substitution is to send a problem from the world of X to another world. Typically, well, it's the world of U, all right? And that's to turn a hard-looking problem into an easy-looking problem, right? That is, if you look at this integral, do the U substitution, change the limits, and you get this way simpler integral, right? But what does that really mean anyway? So, in this case, what we're doing, we're twisting the region of integration when we send it. This is the new region in the new world, no longer in the world of xy, but rather in the world of u. Let me call this v, right? Let me call this v, if you will. And that's an easier problem to solve, and that's the graphical representation. So in general, what we do is we have a problem in the world of xy. Do the substitution to go to the world of uv, and then once we're done with the problem, we go back to the world of xy, or to the world of x, which is in general how we do in Calc 1. Well, but how do we do this with double integrals and potentially triple, quadruple, quintuple integrals? Well, so it turns out, for instance, we already did this substitution on a double and a triple integral, but we were doing it for individual integrals, not for a double integral to do u and v substitution. So for instance, when we evaluated these triple integrals, we did a substitution, say, for the rho function, right? And we did a u equals rho q, whatever the like, and then blah, 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 change the limits and all that. But the other two integrals remain untouched, so we were doing one iteration at a time. That's still a u substitution like in Calc 1 contained in a triple integral. However, for a double integral, we're going to do what we call a u and v substitution. So we're going to do a change of variables, taking both variables at the same time in consideration. How is that? Well, what do we need for this? We need to compute what we call the Jacobian determinant. Well, what is that? Well, if we're given a transformation to go from the world of x to the world of from the world of xy to the world of uv, okay? So we need to compute the Jacobian, the determinant of the Jacobian matrix, which is a square matrix, a 2x2 matrix for the double integral case, which is the partial derivatives of the x equations with respect to u and v, and the partial derivatives of the y equations with both respect u and v. And well, you might remember how we evaluate a 2x2 determinant. That's the product of the main of the elements along the main diagonal, which is this, minus the product of the elements along the secondary diagonal. But what is this Jacobian determinant? Well, so let's look at the generalized double integral here. All right. So again, if we define a transformation from one set to another set, that is a set that defines the points in the xy plane to another set that defines points, equivalent points in the UV plane. Well, for those of you who are who have taken linear algebra, you might have done this linear transformation, that is set of vectors that are equivalent in different universes. You know, it's like the multiverse of integrals. That's what we're gonna do. Transform one integral into another. Okay, so for the double integral case, we want to integrate this. We want to evaluate this double integral. But rather than doing a u substitution, one variable at a time, we're going to do a double substitution, a uv substitution. That means every instance of x is going to be a function of u and v, and every instance of y is going to be another function of u and v. Remember, you might remember, for instance, when you evaluated this integral, that is the integral of e to the, say, x squared, x dx, all right? So this is a very good candidate to do a u substitution, right? So I'm going to do, okay, so u equals to x squared, and du equals, what's that? That's 2x, right? Dx. So that means du will be, what's that? X dx equals 1/2 du. So when we write this integral, what do we do? The integral of e to the u, 1/2 du. So that factor that compensates the u du part of the problem. So, okay, what is that? Okay, let's say we're integrated between 0 and 4. Okay, between 0 and 4. Okay. And what is that going to do in this case? Well, the limits of integration are going to go this time between 0 and 16. All right? 0 and 16. Okay, so think about that 1/2 multiplying the e to the u. What is that 1/2 going to do to the function e to the u? Think about pre-calculus or basic algebra, when you learn all about these transformations and horizontal and vertical shrinkings and stretchings. What is that 1/2 going to do? Okay, when you have a negative in front of a function, that flips it upside down, right? But when you multiply by a fraction between 0 and 1, what's the effect on the original function? It shrinks it vertically, right? So we're going from, okay, that's e to the x squared, like this, okay, from 0 to 4. In the xy plane. And this is going to shrink it like this, right? It's going to go between 0 and 16. And it turns out these two areas are equivalent, right? That's what we're doing when we're sending a problem from the world of x to the world of u. But again, did you ever wonder what is this factor that compensates? It's the Jacobian. They never told you that in Calc 1, but it's the Jacobian. So every time you're doing a u substitution, ever since Calculus 1, when you do it in Calculus 2, you have been doing the Jacobian, but they never told you. It's a one-dimensional Jacobian. That is a factor that shrinks or stretches the original region in the new equivalent world. Well, in this case, it's going to be the UV world, right? So, yes, in a way you have been working with the Jacobian, but you didn't know about it. Well, how do we compute the Jacobian? Well, let's have a look at some examples of computing the Jacobian, and then we're going to evaluate a couple of integrals. Okay, so they're asking us to compute the Jacobian of the transformation from the rectangular to polar. All right, so we need to set, first of all, a transformation. That is, the transformation big T, where x equals r cosine theta and y equals r sine theta. You know these conversion formulas from the world of polar, right? Okay. Let's get the Jacobian. J of r theta. All right. Okay. So that means, okay, we need to take the partial of x with respect r, the partial of x with respect theta, the partial of y with respect r, and the partial of y with respect theta. So how about we compute these partial derivatives? Okay, let's have a look at the x equation. Find the derivative of x with respect r. Okay, the derivative of r is 1 times cosine, that equals cosine theta. The derivative of the x equation with respect to the angle theta, well, the derivative of cosine is in that negative sign, times the r, that's negative r sine theta. Okay? And then what about partial of y, of the y equation with respect r? Okay, differentiate r, that's 1 times sine, that's just sine theta. And the derivative of the y equation with respect theta, that's the derivative of sine, which is cosine, times the r that's there, that's r cosine theta. How about we compute these 2 by 2 determinants? Right? Okay. Product of the elements along the main diagonal, that means cosine theta times r cosine theta minus negative r sine theta times sine theta. Okay? What is that going to give us? Oh, check this out. R cosine square theta minus minus becomes plus r sine square theta. Common factor, that's r. That's going to leave us with cosine square theta plus sine squared theta, which is equal to 1. R times 1, that equals to r. I wonder what's the meaning of that r. Okay, so remember when we first described these integrals, like these integrals in polar? Okay, so we started with a double integral of f of x y dA. So we always start with an integral in rectangular coordinates, right? But then we want to do the conversion to polar. What do we do with the conversion to polar? Okay, so we're going to start at a set r, and then we're going to send this to the world. Let me call this S. Okay, we're going to go from the world of r to the world of S. Now, what do we do? Well, every instance of x in your integrand, I mean, if you had an integral with an f of x and not an area integral, so every x becomes some r cosine theta, and every instance of y becomes r sine theta. All right? And then, well, since this dA becomes either dy dx or dx dy, depending on how we iterate the double integral, well, what do we do in the world of polar? Well, we should do simply dr d theta, right? But remember that factor of r right here? What do you think it is now? It's the Jacobian, right? It's that 1/2 here in the example I gave you with the example that shrinks or twists the entire region. That's what it does, right? So that's the power of this Jacobian matrix, to get that compensation factor to get the equivalent points from the world of xy to the world of u. V, well, in this case it's r theta. It's more applied to the polar system, right? So, well, actually, we derived this using geometry. Remember the pizza slice, the twisted rectangle, all right? So the area, it was no longer delta r times delta theta. In a similar way, it would have been delta y and delta x. So we needed that twisting factor to turn that rectangle into a circular or polar rectangle. What do we need to twist it? Multiply by the factor of r. In a similar way that we needed to multiply this region by a half to get the equivalent area, but in this case, it's to solve a problem in an easier way, right? So now you have another way to derive the element of area for the polar system. simply find the Jacobian of the transformations here. All right, okay, one more. Okay, one more, and then we go on a break. Example number 2. Sketch the region R in the xy plane given by the inequality y greater than or equal 0, less than or equal the square root of 1 minus x squared. Sketch this corresponding region in the S in the R theta plane. Interesting. What are we going to do here? So number 1, what does that represent? Semicircle, which one? The upper or the lower? The upper. Is it the entire upper semicircle? No, which part? Oh, also I needed, yeah. 0, x, and 1. Yeah. That's the second piece of information I forgot to type. So what's part of the upper semicircle? The left part or the right part? The right part, right? Because it's from 0 to 1, all right? So that means it's going to be this. Okay, there you go. Much better. Okay, it's going to be this region, right? I will shade it. And I'm going to call this I'm going to call this our region R. Okay? Now, this is what we're going to do. What does that represent in the world of polar? So you guys can visually get the limits, the bounds in the world of polar. You know how to read radius, how to read an angle, right? So now we're going to go from the world of S to the world of, no, from the world of R to the world of S. So what are the limits? Think of the domain of integration. What are the limits of R? How is R varying in this case? From where to where? 0 to 1, all right? 0 to 1. All right? And what about the angle? How is theta varying? 0 to pi halves, right? Or pi over 2. Okay. Now let's define this region. Okay, do you see how those limits are numbers, are constants? What geometric shape do you obtain when your limits of integration are just constants? A rectangle, right? A rectangle. Don't we love rectangular regions to integrate over because those are the easiest ones to integrate. That's why we do all this change of coordinates, because we are going to turn complicated regions into rectangular regions that are the easiest ones to work with. All right, so let me create a whole new world here. What's the new world? That'll be the world of our theta. So R is going to vary between 0 and 1, right? And what about 0 to pi over 2? Okay, let me do it a little higher, maybe. That's 1, that's also 1, maybe here. So, that's 0 to 1, that's pi over 2. All right? Let me shade the region a different color. And let me call this our region S. So now you'll have a different perspective of this change of coordinates. So how do you like that second region? Even still, this quarter of a circle or region, it's not too complicated to integrate over, but it's still a lot better to integrate over the rectangular region, right? So what did we do here if we were to integrate this? Let's find the area. I'm not going to calculate. I'm just going to set up the integral. So area equals the double integral over the region R, okay? That is dA, which means That's the double integral. I'm going to go dy dx from 0 to the square root of 1 minus x squared, and from 0 to 1. All right, that would be the integral to compute the area of that region. But I mean, look at that integral. Do you want to do a trig substitution? It's an easy trig substitution. You can easily do it. But we can bypass that trig substitution by taking advantage of those new tools we learned in this class, that is changing the coordinates to polar coordinates. So now I'm going to go to the world of S, all right? I'm going to go to the world of S by iterating the integral in the world of polar. So rather than integrating from 0 to 1 and 0 to this humongous radical, I'm going to integrate from 0 to 1 and from 0 to pi over 2. Well, you guys are familiar with this already, with this change of coordinates. But what does that dy dx become? Will that just become dr d theta? What do I need? R. That is, what is that? The Jacobian, right? So, but we didn't talk about the Jacobian earlier. I just gave you the geometric point of view, the pizza slice, to show you where is this R coming from. All right? Again, in a similar way that we needed to multiply by a half to integrate over this region, complicated integral, U substitution, compensation factor. This is the one-dimensional Jacobian, if you want to call it somehow. So, but that's just only a compensation factor you'll learn about in Calculus 1 to stand the U part of the problem, change the limits. What does that mean geometrically? Well, we shrink the height of the function, but we stretch the little interval of integration to make sure these two areas are still the same. So that in the world of U, we work on an easier problem, right? And then once we solve the problem, we go back to the world of X. How do we evaluate these integrals? Well, let's take a break and we'll come back.